Welcome back, guys. In this video we are discussing the gradient of a function of n variables and how we might interpret that, and we'll also discuss and compute some second partial derivatives of a function of two variables. We'll discuss the form of the second partial derivatives of a function of three variables, and we'll discuss the form of the second partial derivative of a function of a function of n variables. So let me just give you an example of a gradient of a function of n variables. So let's say we've got temperature in a room. So we'll say W is representing temperature, and it's given by this notation, capital T of X, Y, and Z. So I can't actually graph this temperature function. It is a function of three variables, so its graph lives in four-dimensional space. The graph would consist of points X, Y, and Z, and then the W that goes with each of those X, Y's, and Z's, so T of X, Y, and Z. So we've got four coordinates, so I can't really graph this. But I think that we all can wrap our minds around the idea of a temperature gradient. So I can take the gradient of this function. It's a function of three variables, so that gradient is going to have three components. I'll have the partial of t with respect to x as a function of x, y, and z, the partial of t with respect to y as a function of x, y, and z, and the partial of t with respect to z as a function of x, y, and z. So each of those is giving me a formula for the instantaneous rate of change of temperature in the x direction, y direction, and z direction, provided that we're talking about temperature at a particular location, x, y, z, in some room. Now, if I want the gradient at a particular point, well, I just, of course, substitute in that point, x naught, y naught, z naught. Now at this point, it doesn't really make sense to call this the direction of steepest ascent, because when I graph this, I'm not graphing a single surface, I'm graphing a hypersurface. It lives in four-dimensional space. So this doesn't really make sense geometrically as a direction of steepest ascent anymore. But I think conceptually it makes sense to all of us. What this is saying is, if you want to maximize the temperature as much as possible, and you're at the location x naught, y naught, z naught, you should head in this direction. I want to say maximize temperature. Say maximize the rate of change of temperature. Increase the temperature is more accurate. Increase the temperature as much as possible. Head in the direction of this vector from x naught, y naught, z naught. And then if you're wondering, well, what's the rate of change of temperature as I go in that direction? The rate of change of temperature is, well, it's the maximum rate of change of temperature in any direction. So it's going to be the maximum directional derivative of our temperature function at that point. And the maximum value of the directional derivative is still the magnitude of the gradient. Now this has nothing to do with slope per se, although we can interpret all of these derivatives as slopes, but they're slopes of a hypersurface that we can't really see. But I think this makes sense. It's saying, okay, you're in a room, every x, y, and z is associated with a particular temperature. If I am at this location, x naught, y naught, z naught, and I want to increase my temperature as much as possible, there's some vector that tells me which way to go to increase my temperature as much as possible. Go in that direction. So maybe the gradient vector looks like this. Maybe that's the direction where temperature would increase as much as possible. So they're saying go that way, and then you say, okay, if I do go that way, what is the rate of increase in temperature as I take one step in that direction? The rate of the instantaneous rate of change of temperature as I make a 1 unit change along this direction of greatest increase is this, the magnitude of the gradient function evaluated at that point. So this is the direction of greatest increase we can't really think of it as the direction of steepest ascent because we're not talking about a surface anymore. We're talking about this hypersurface that we can't see. And the maximum value of the instantaneous rate of change from x naught, y naught, z naught is the magnitude of that gradient. Okay, and again, remember, gradient is a vector, it's a direction. But if I want slope, if I want instantaneous rate of change, I've got to find the absolute, or not absolute value, excuse me, the magnitude of that gradient. So this instantaneous rate of change, that's going to be a scalar. Positive, negative, 0, I don't know what it is, but it's a scalar. Geometrically, we tend to think of it as slope. When we can't think of it as slope anymore, it's the maximum rate of change of temperature in any direction from x naught, y naught, z naught. And it turns out that if I want to increase my temperature as much as possible, I go this way, and the rate of increase in that direction is given by the magnitude of the gradient evaluated at that point. Okay, so in general, so that's an application problem. Of course, we don't always work with applications, but we can always talk about hypersurfaces. That's fine. If W is a function of n variables, could be 2, could be 3, could be 15 variables, that'd be fine. The gradient of f, if it has n variables, that gradient has n components. It's the partial of f with respect to x1 plus the partial of f with respect to x2 and the partial of f with respect to x sub 3 and so on, partial of f with respect to x sub n. So we've got n components here. Each one is a formula for the instantaneous change in f as this changes by 1 unit, as the variable in the subscript changes by 1 unit, and all the other variables are held constant. Now, if I want to increase f as much as possible at a particular point, I evaluate this at a particular point. I'm going to write x sub 1 naught, x sub 2 naught. Sorry for the strange notation, x sub n naught. But that's a particular point. That is the direction of greatest increase. And you might say, what do we mean by direction? I don't know. We're in n-dimensional space. But if we let x1, x2, x3, all the way through xn change by this much, and we head in that direction, the function values are going to increase as much as possible. And again, this is a vector, it's not a scalar. If I want to know, like, what's the maximum instantaneous rate of change of f in any direction from this particular point, the maximum value of the directional derivative at that point, which represents the maximum instantaneous rate of change of f at that point in any direction. Oops, that says x sub n sub 0. That's going to be the magnitude of the gradient evaluated at the point of interest. Don't let all of the strange subscripts bother you. That's just a point, that's just a point, that's just a point. It's just a particular point in n-dimensional space. But if I go in this direction, that's where my f is going to increase as much as possible if I want the slope in that direction or the instantaneous rate of change of this function in that direction. It's just the magnitude of the gradient at that point. Okay, so that is the first topic for this video. Wanted to talk about gradients of functions of n variables and what they mean. So we can't talk about them geometrically anymore, but we can still interpret them. Now let's talk about second partials. In the last video, we looked at first partial derivatives of this function given by z equals f of xy, which is natural log of x squared minus y. And we found the first partial with respect to x. And we found the first partial with respect to y. And remember, even before we compute these are formulas for the slope in the x and y direction at any point. And then we can plug in the xy point, the point that we're interested in, and we can find the slope at that particular point in the x and y direction. For each of these, we had to use the chain rule, because I've got a function inside my logarithmic function, and it depends on x and y. So the partial with respect to x of this, of log of a function, is 1 over the function by the chain rule, times the derivative of the inside with respect to x, treating y as a constant. And we've already done this. Derivative of x squared is 2x. Since there's no x in this, derivative of negative y is 0. So we just ended up with 2x divided by x squared minus y. And if you're wondering how that got into the numerator, I just wrote that as a 2x over 1 and I multiplied straight across. I know it looks like it's way down here right now, but it's not. It's really that, or 1 over this times 2x over 1, and when you multiply straight across you get this. So this is a formula for the slope in the x direction at any xy in the domain of the function. This is the slope of the surface in the x direction. And remember, we know we're talking about a surface because every xy here is associated with a z. So I don't know exactly what it looks like, but I know that if I take any xy in the domain, every xy goes to a z value, and it gives me something like that. So this is a formula for the slope of the surface in the x direction. You plug in the point that gives you the slope in the x direction at that particular location. Similarly, we took the derivative of this using the chain rule. The derivative of log of a function that has a y in it with respect to y, treating x as a constant, is 1 over the inside function times the derivative of the inside with respect to y, treating x as a constant, by the chain rule, And the derivative of x squared with respect to y is just 0 because there's no y's in it. If x is a constant, this might as well be a 3 squared. Derivative of 9 with respect to y is 0. So the derivative of x squared with respect to y, if x is a constant, is 0. So just get a 0 and a negative 1 here. Derivative of negative y with respect to y is just its coefficient of negative 1. And again, we multiply straight across. We've got this fraction times negative 1. So I've got this. And again, this is the formula for the slope of the surface in the x direction. Now, just as a brief review, remember from Calc 1, when you're taking first derivatives, if f prime is positive, that means the function is increasing at that particular x value. Let's say f prime of x naught is positive. So here's my graph, here's x naught, f prime of x naught is positive. If I draw the tangent line, it has a positive slope. The graph is increasing there. You look at it from left to right, it's going up. That means it's increasing. And remember from Calculus 1, if the derivative is negative at a point, that just means the function is decreasing there. If I draw my tangent line, if I look at it from left to right, that slope is negative. So the function is going down. And I'm focusing on a particular x value rather than an interval. But just remember, first derivative is positive, it means it's going up. First derivative is negative, it means it's going down. First derivative is 0. We have a couple of possibilities. We might have a first derivative of 0 at a min or at a max. Or at a little flat point. Maybe it's decreasing for a while, then it's flat, and then it's decreasing again. So if I draw the tangent line here at the bottom, it's a horizontal tangent line, its slope is 0. Tangent line at the top has a slope of 0, and this tangent line has a slope of 0. So if you get a derivative of 0 at x naught, that means you're either at a min or a max or possibly a flat point. But if the derivative is positive, the function's increasing. If the derivative is negative, it's decreasing. Now, in Calculus 3, these are functions of several variables. So when I plug in a particular x-y pair over here, I'm going to get a number. That number is going to be positive, negative, or 0. We interpret it in the same way that we did in Calculus 1. We just have to remember this is slope in the x direction. So when we plugged in 2, 3 to this last time, so I replace the x with a 2. Here's my formula. And I replace the y with a 3. Order of operations, make sure you do this first. 2 squared is 4, 4 minus 3 is 1. 4 divided by 1 is 4. Then we did the same thing. We evaluated the derivative at 2, 3. The partial derivative of f with respect to y at 2, 3. And we got this. That's still 4 minus 3 is 1. Negative 1 divided by 1 is negative 1. So this is slope in the x direction at xy equals 2, 3. And this is slope in the y direction at xy equals 2, 3. Since this is positive, that means the z values are increasing. As we head in the x direction from the point 2, 3. And this means the z-values are decreasing. Not as much as they're increasing in the x direction, but the z-values are decreasing in the y direction. So you go a little bit in the y direction, the z's are going down. As long as we're starting at the point 2, 3. Okay. So now we remember from Calculus 1, first derivative means the function's increasing. Or first derivative is being positive, that means positive slope, that means the function's increasing at that location. If the first derivative is negative, that means we've got a negative slope, that means the function is decreasing at that location. Zero slope means we could have a min or a max or a flat point like that. We interpret first derivatives in Calculus 3 the same way. Now let's talk about second derivatives. Now back in Calculus 1, you learned that if the second derivative was positive at a particular point, the graph was concave up at that point. Now whenever I draw this picture, I'm never really sure where to draw that x naught. Because x naught could be any point in here. This graph is concave up for all of these x values. So every point on this interval could be x naught. This is concave up. It looks like a cup facing up. And you might say, how do you know that it all has a second derivative that's positive? Well, remember the first derivative is 0 down here. So that's f prime is 0. And then on this side, f prime is positive because those slopes are increasing. If you look at the tangent line, they rise from left to right. On this side, the slopes are negative because the function is decreasing. So the function values of f prime are going from negative to 0 to positive. So if it's going from a negative number to a 0 number to a positive number, f prime is increasing. And if f prime is increasing, that means that f double prime is positive, because f double prime is the rate of change of the rate of change. Okay, so that's concave up. Intuitively, whenever I see second derivative positive, I think it looks like a cup facing up, concave up, because, well, f prime is increasing. Our derivatives are going from negative to 0 to positive, so they're going up. The derivatives are going up. Now, f double prime at a point being negative, that just means the graph is concave down. Looks like a cup facing down. And we can use a similar argument. F prime is 0 at the top, f prime is positive on this side and negative on this side. So f prime goes from positive to 0 to negative. So it was a positive number, and then it was shrinking until it was a 0, and then it was shrinking until it was a negative number. So as you go from left to right, f prime is decreasing because I went from a positive to a 0 to a negative. And f double prime is the rate of change of f prime. So it's the rate of change of the rate of change. So if f prime is decreasing, that means f double prime must be negative, because when something is decreasing, its derivative is negative. Okay, so concave up looks like this, concave down looks like this. If you have a second derivative that is 0, usually you're switching between concave up or concave down. I'm not going to worry about that picture. But let's talk about second partials now. Second partial with respect to x and y can be interpreted the same way. We just have to remember the direction that we're going in. So if I take the derivative of this partial with respect to x again, I get what's called the second partial of f with respect to x. That's going to give me some sense of concavity, whether it's concave up or concave down in the x direction. First I'll get a formula for that concavity, and then I'll plug in the point, and then at that point I can find out, is the graph concave up in that direction or concave down in that direction. So let's calculate. Let's do a little bit of computation and then interpretation. So f sub x was 2x over x squared minus y. That means the partial of f with respect to x, or the second partial of f with respect to x, is this. Now, I did not talk about Leibniz notation yet. I like subscript notation with this because it tells you take the derivative with respect to x and then take the derivative with respect to x. You read it left to right. With Leibniz notation, it's a little different. You sort of read it right to left, but it's because it's an operator. It doesn't matter in this case, but it'll matter later. This says take the derivative of f with respect to x, partial derivative of f with respect to x, treating y as a constant and any other variables as constants, and then take the partial derivative of that result with respect to x again. So here's the shorthand. We call this the second partial. Sometimes people will call it the second partial derivative of f with respect to, that's my abbreviation for with respect to x. But sometimes you won't even, people will stop saying the word derivative. They'll just call it the second partial of f with respect to x, but it's really a second partial derivative. It's an instantaneous rate of change of the rate of change. So this is giving me a sense of concavity in the x direction. And first, it's just a formula for, I'm going to say concavity in the x direction. When you plug in that point, that's going to tell you whether the graph is concave up, concave down, or maybe switching from concave up to concave down at a particular xy location. Okay, so let's compute the second partial of f with respect to x for this function. So I want the partial with respect to x of the partial of f with respect to x, which we already calculated. So that was 2x over x squared minus y. Now I've got a function of x in the numerator and another one in the denominator. So because of that, it's appropriate to use the quotient rule here. If either one of those was a constant with respect to x, I'd probably rewrite it and then just use a constant multiple rule. But since there are no constants with respect to x here, I've got a function of x, an explicit function of x divided by an explicit function of x. I'm going to use a quotient rule. So according to the quotient rule, the derivative of this is the bottom function times the derivative of the top function with respect to x, treating y as a constant. So that's low d high, you probably remember this from Calc 1, minus high, top function, d low, partial with respect to x, treating y as a constant, all over low low, bottom function squared. And remember, the d's apply to what's in front of them. It's an operator. This is the derivative of low over high is equal to this. That's our quotient rule mnemonic. I like to write it out like this and then just remind myself in this other color that I still have a derivative to compute here and a derivative to compute there. So let's do it. The derivative of a constant times x with respect to x is just the constant. The derivative of x squared with respect to x is 2x. The derivative of negative y with respect to x is 0. So we've got this. Now if I distribute my 2, I've got 2x squared minus 2y minus 2x times 2x is negative 4x squared over x squared minus y, quantity squared, and 2x squared minus 4x squared is negative 2x squared. You could leave it like this. If you prefer, you can factor it. We could factor out a negative 2. And usually we like to write our letters in alphabetical order. All right. So that's the second partial of f with respect to x. Again, this is a formula for concavity. When I substitute in the point x equals 2, y equals 3, I'm talking about a particular point on my surface, I get this. X is 2, y is 3. 4 minus 3 is 1. 1 squared is 1. So I have negative 2 times 4 plus 3 is 7. So negative 14. That's very negative. So since that value is concave down, or is negative, we know that the graph of the surface is concave down in the x direction, but only at that point. I mean, this concavity is going to change from x naught, y naught to x naught, y naught. Similarly, we can calculate the second partial of f with respect to y. So you take the partial with respect to y of the partial of f with respect to y. Which you can write this way. This gives you concavity, or a formula for concavity in the y direction. We have to plug in a point if we want to know whether the graph is concave up or concave down at that point in the y direction. And this time, we did our calculations earlier. The partial of f with respect to y was negative 1 over x squared minus y. Now this time it makes more sense to bring this up to the numerator and then change that implied 1 there to a negative 1 power. The reason it makes more sense to do that is because this negative 1 is just a constant. So I can think of this as negative 1 times the quantity x minus y to the negative 1 power. And now I just have to use the chain rule rather than the quotient rule. So according to the chain rule, well, my outside function is this negative function to the negative 1. Here's my inside function. The derivative of the outside is given by the power rule. I do negative 1 times negative 1 is positive 1, times my inside function, substitute it back in without taking the derivative, evaluated to the 1 less power. So I did negative 1 times negative 1 is positive 1, then I have my inside function to the negative 1 minus 1 power by the power rule. Negative 1 minus 1 is negative 2. And then we multiply by the derivative of the inside with respect to y, treating x as a constant, by the chain rule. There are no y's here, so the derivative of this is 0. The derivative of negative y with respect to y is just negative 1. So we end up with negative 1 times this quantity, or I think it's still easier to rewrite it this way. I think in terms of positive exponents, not negative exponents, although I'm comfortable converting them. So I like to write it this way and then evaluate at a particular point. So this is a formula for the concavity in the y direction. If you give me an xy in the domain, I can plug it in and I can find out the concavity in the y direction at that point. So let's evaluate this at x equals 2, y equals 3. When x is 2, we get this. Y is 3, we get that. So this is 1 squared, which is 1. So we get negative 1. So that means the surface is concave down in the y direction. At that particular point. Okay. Now there are other partial derivatives that we have not talked about. They're called mixed partial derivatives, or excuse me, mixed. These are other second partial derivatives. We took the derivative with respect to x twice, and we took the derivative with respect to y twice, but it's also possible to take the derivative with respect to x, and then take the derivative with respect to y. I like the subscript notation for this because it just says, you read it left to right, it says take the derivative with respect to x first and then y. Leibniz notation, it looks reversed, but if you think about it in terms of operators, it still makes sense. This says, take the derivative of f with respect to x, and then take its derivative with respect to y. So if I multiply these together, and it's not exactly multiplication, but it's just notation for that, we see it this way. Notice that there's a yx here and there's an xy there. That's because of the way this is read. You take the derivative of f with respect to this variable first, and then you take the derivative of that result with respect to y. So let's compute this, and then we'll talk about what it means. So for our function, we had the partial of f with respect to x was 2x over x squared minus y. And I want to take the derivative of that with respect to y now to get a mixed partial. So take the derivative with respect to y of the partial of f with respect to x, which is this. Notice that there's only a y in the denominator. So that means this 2x is constant with respect to y. And if it's constant, I think I want to pull this denominator up and then just use the chain rule and the power rule in order to evaluate the derivative. Oops, I'm sorry. Right now, that's an implied x squared minus y to the first. When I bring that up to the numerator, the 2x is a constant, and I end up with x squared minus y to the negative first. As I change that positive 1 to a negative 1. Now, since x is a constant, you factor that out. And now you're taking the derivative of x squared minus y to the negative 1 with respect to y, treating x as a constant. Now, since x was a constant, I factored it out in much the same way that we would factor out a constant if I had 2 times x plus 1 to the negative 1. I'd factor out the 2 because the 2 is constant. And then I would take the derivative of this part. I'd get negative 1 times my inside function to the negative 2 times the derivative of the inside, which happens to be 1. That's a Calc 1 derivative. This is the same. It looks different, but it's the same. There's no y in this. These variables don't match, so that's a constant. Pull it out just like you pulled out the 2. Okay. Now over here, I've got an inside function. So if I want the derivative of this with respect to y, I take, well, I've got a function to the negative 1 power. It's going to be negative 1 times the function to the negative 2. Put your inside function back inside, and then multiply by the derivative of the inside with respect to y, treating x as a constant. If x is constant, this is 0, and we just get a negative 1 here. That negative 1 times that negative 1 is positive 1, and we get 2x over x squared minus y quantity squared. Okay, this is a formula, and if I want to evaluate it at a particular point, x equals 2, y equals 3, I get this. That's 1 squared, so I get 1, so that's 4. Say, oh gosh, what does that mean? Well, this notation up here is a clue to what it means. This is the slope of the surface in the x direction. We're asking here, how does the slope of the surface in the x direction change as y changes? So this is the instantaneous rate of change of the slope of the surface in the x direction as y changes. So I've got some surface over here, and that's not what natural log of x minus, or x squared minus y looks like, but I've got my cartoon surface that helps us understand these ideas. If I want slope in the x direction, at x naught, y naught. So I go to x naught, y naught, and then I find the corresponding point on the surface. So maybe that's our point at x naught, y naught. To find the slope in the x direction, we intersected the surface with a plane that was parallel to the xz plane over here. So I usually try to draw a plane. I'm not going to try to draw it this time because I think it's going to mess up our picture. This is slope of the surface, or this is the plane, y equals y naught, and then we're saying, well, what happens to the z values there on the surface? As we go in the x direction, it looks like the slope is negative. Now if I want the slope in the y direction, I let x equal x naught, and that gives me a different plane. And I look at the slope of the surface in the the y direction, and we're going in the positive y direction, which is over here. And I say, what happens to the z values there? It looks like the z's are going down. Well, this is asking about how does the slope of the surface in the x direction change? And the slope of the surface in the x direction is given by this, right? I look at this curve and then I look at the slope there. How does that slope change as y increases by 1 unit? So we're going over this way, 1 unit, and we're calculating the slope over here. And we're asking ourselves, is that slope increase or does that slope decrease? If that slope increases, this mixed partial is positive. If the slope decreases, this mixed partial is negative. Similarly, if I take the derivative with respect to y and then x, this is the other mixed partial for a function of two variables. So you take the derivative with respect to y first, and then you take the derivative with respect to x. Well then, you're looking at the slope in the y direction, and you're looking at how that changes as you move 1 unit in the x direction. So this is the instantaneous rate of change of slope of the surface in the y direction as x changes by 1 unit. So remember, our point of interest was right here. When I wanted to know this rate of change, so I said, how does the slope in the x direction change as y increases? I found the slope in the x direction at the purple dot, and then I went 1 unit in the y direction and I found a slope in that direction. And I said, okay, well, how are the slopes changing? Of course, we're talking about instantaneous rate of change, but still, this helps you. It's an estimate. It'll help us to estimate this rate of change over here. Now, when I'm talking about this one, it's the slope of the surface in the y direction. So to find the slope in the y direction, I had to let x equal a constant. It gave me that blue line. And I found the slope here. Then we're saying to ourselves, okay, let x increase by a little bit. We're saying, okay, I find the slope here in the y direction, and then I find the slope here in the y direction. Is this slope in the y direction greater than or less than this slope in the y direction? It looks like they're both negative, but I think this one is less negative. So it looks to me like the slopes are increasing. So I think this second partial with respect to y and then x would be positive because this slope is increasing as I go from left to right. Now, it turns out if your function is nice and smooth, if these partial derivatives are continuous, and we always say on an open disk, it just means in a region around a particular point. So we don't want to worry about boundaries of our surface or anything like that. It turns out if the derivatives are continuous, these mixed partials happen to be equal to each other. So if you take the derivative with respect to x and then y, it turns out to be the same as taking the derivative with respect to y and then x every time. Let's verify that for the example function. We took the derivative with respect to x, and then we took its derivative with respect to y, and we got this. And then we plugged in our point 2, 3, and we got the slope the rate of change of the slope in the x direction as y changes is 4. So I'm looking at the pink curve. Slope in the x direction is increasing by 4 units approximately as we go 1 unit in the y direction. Let's see what happens if you do it the other way. Hopefully you also get 4 and you also get the same formula. So we start with the partial of f with respect to y this time, which is negative 1 over x squared minus y. And we're taking its derivative with respect to x. So I've got derivative of this guy with respect to x. I'm going to, since that's a negative 1 in the numerator, which is a constant, I'll write that as x squared minus y to the first and bring that up to the numerator, so I don't have to use the quotient rule. It's not necessary here. And I'm taking the derivative with respect to x now, treating y as a constant. Well, I've got to use the chain rule again, because I've got a function nested inside another function. First, I do derivative of the outside. Negative 1 times negative 1 is positive 1. Evaluated at the inside. Oh, excuse me, I should have talked about the exponent. The derivative of something to the negative 1 power is, well, the derivative of negative 1 times a function to the negative 1 power is negative 1 times negative 1, which is positive 1, times the function to the negative 2. Put the inside function back inside, and then multiply by the derivative of the inside by the chain rule. And the derivative of x squared with respect to x is 2x. Derivative of y with respect to x, there's no x's in it, so it's 0. So we get the same formula that we got before. I've got a 2x and an x squared minus y quantity squared in the denominator. I sure do. Our partials are continuous, everything is nice and smooth, and because of that, these derivatives are the same. These mixed partials are the same. Okay. Now, some people say, well, why is this the same? I heard a great argument from one of my students. He said, I think the reason they're the same is that if you're taking the derivative with respect to x and then y, the only terms that show up are terms that have x's and y's in them. Otherwise, they're just going to go to 0. And he said, if you end up with terms that have x's and y's in them, well, it doesn't matter if you take the derivative with respect to x first and then y, or y first and then x. You're eventually going to end up doing all the same types of things. So I thought that was a great argument that he made in class the other day. Another argument that I've heard often, and it's a geometric argument, and it's a little bit hand-wavy, sorry about that, is, okay, this is asking about the rate of change of the partial of f with respect to x. So it's the rate of change of the slope in the x direction as y changes. So I'm starting at this purple point, and I'm going in the x direction and then in the y direction, and I end up right here. Over here, I'm starting at the purple point, and I'm looking at the rate of change in the y direction, and then I'm seeing how x changes. So whether I change x first and then y, or if I change y first and then x, I still end up at the same location. And it still hasn't proven that these are going to have to be equal to each other, but there's something about that, the fact that we end up at the same location, that would make me suspect that these two functions have to be equal to each other. Okay, so that's for functions of two variables. And functions of two variables correspond to surfaces. Now, if you have functions of n variables, we can't interpret all of these geometrically in the same way, but we can still interpret everything in terms of rate of change. So if I have w as a function of x, y, and z, it's got 3 first partials now. And when I say first partials, I mean first partial derivatives. But I've got a partial with respect to x, a partial with respect to y, and a partial with respect to z. And when I put them together, I end up with this multi-dimensional analog of the first derivative. It's the gradient vector. It points in the direction of greatest increase of our function f of x, y, z, If you head in this direction, W is going to increase as much as possible. If you want the rate of increase in that direction, you take the magnitude. That's what we do with our first partials, and these individually give us instantaneous rates of change in f as x changes while y and z are held constant, as y changes when x and z are held constant, and when z changes and x and y are held constant. Now when you do the second partials this time, you've got three variables. So you've already taken a derivative with respect to x. Now you could take its derivative with respect to x, y, or z. So you take the partial with respect to x and then x, partial with respect to x and then y, or partial with respect to x and then z. Or you could take the partial with respect to y and then x, or partial with respect to y and then y, or the partial with respect to y and then z. Or you can imagine how this goes. I take the derivative with respect to z, and then I could take the derivative with respect to x, with respect to y, or with respect to z. So we started with 3 variables. We end up with 9 partial derivatives. Many of those are the same because the mixed partials tend to be equal as well, as long as our function is well behaved enough, as long as our partials are continuous, I believe is the condition. You should look that up in your book because I'm not 100% sure. Yeah, if you start with a function of 2 variables, you get 2 partial derivatives and 4 second partial derivatives. With a function of 3 variables, you get 3 first partials and 9 second partials. Can you imagine how many third partials? Just multiply by 3 again, you're going to have 27 third partials. Just a lot. If you have n of them, you're going to have n second, or if you have n variables, write that down. Oops, not enough room on that page. So let's say we've got a function of n variables. Now you've got n first partials. And each of those can be differentiated n more times to get second partials. So you have n squared second partials. Now, our multidimensional analog of the derivative is called the gradient. It's the vector of first partial derivatives. And this next word I am about to mispronounce. I am still not 100% sure how to pronounce this because I've said it many times and somebody has said, no, not like that, like this. And I'm like, I swear I'm hearing the same thing twice. The matrix of second partials is an n by n matrix. And it looks like the Hessian. But there's something about the way I'm pronouncing that that's incorrect, and I'm not sure what it is. But we take the partial with respect to x1 twice, take the partial with respect to x1, then x2, and you go all the way across, partial with respect to x sub 1 and x sub n. Then you go take the derivative with respect to x2, and then x1, and then x2, and then x2, and then x2, and then xn. And you keep going like this until you end up with n rows. Take the partial with respect to x1, x sub n, and then x sub 1. And eventually you have the partial with respect to x sub n and x sub n. So you've got this n by n matrix. This is the it's the n by n matrix of second partials. That's what the Hessian is. And this is the multidimensional analog of the second derivative. You might say, what does that mean? Second derivative just gave us concavity. Now we've got all of these different things. We've got concavity in n different directions on some hypersurface. It sounds very mysterious, but all the math works out just fine. It's all very very similar to what you've done previously. But it's just cool to think about. Okay, so that's what you can expect for second partials. Most of the time in this class, we're dealing with a function of two variables. So we have z equals f of x, y. So we've got first partials with respect to x and y, second partials with respect to x, second partials with respect to y. You've got some mixed partials. And these give us, provided we're thinking about z as a function of x and y, so this is a surface, slope in the x direction and y direction. When this is positive, the graph is increasing in the x direction. When it's negative, the graph is decreasing in that direction. Same is true for that. These second partials with respect to x and y give us concavity in the x and y directions. These are a little trickier, and we've interpreted them up here. This is instantaneous rate of change of slope in the x direction. So you start with this, and you say, how does that change as y changes? And this one, you take instantaneous rate of change of slope in the y direction. So you look at slope in the y direction, and you say, how does that change as x changes? Okay, so those are our second partials, guys. Please let me know if you guys have any questions. I'm proud of you. I know this work is really hard. I'm here for you if you need me.